Welcome again to today's class. In today's class, we want to discuss experiment on application of moments. Yes, so it has this objective to determine the mass and density of a meter rule using the principle of moment. Apparatus, mass, meter rule, knife edge, calorimeter filled with water, and vernier caliper. Now, look at the sketch of the diagram. Look at the procedure. The procedure says, place the knife edge at 5.0 cm from the center of gravity you obtained initially. That means, first thing you have to do is to get your meter rule, keep it on a knife edge, and note your word center of gravity. Please note that the center of gravity has range. And so the range could be between 48 to 52 cm, depending on the meter rule you are using. Are you getting it? 48 to 52 cm. So first thing you do is to get your center of gravity. Once you get it, you note it. That is one. Then the mass M provided at the other side of the knife edge. So when you get your center of gravity, if your center of gravity is 50, that means the meter rule balanced at 50 dots at the 50. That means here will be 50, this center will be 50, and you now measure from 50 to this point. That will be your 5. The place you now put your knife edge again will be 5 cm. That the distance from this center of gravity to the point you place your knife edge is 5 cm. So that means if you place it here to be 5 cm, the remaining side will be what? 45 cm. That means from here, knife edge to the end is 45 cm. Now, as you place your mass at the end of the meter rule, as you hang your mass at the end of the meter rule, it will not balance. You are the one to now be shifting that mass you hang here. You have to be shifting it till it keeps this meter rule at equilibrium. It keeps it balanced without shaking anymore. So that is what they mean by adjust the position of the mass M while maintaining the position of the knife edge until you obtain a new balance point. Record the distance between the CG. Record the distance between the CG and knife edge as D1. D1, that is from 50 to this knife edge as D1, that is 5, is constant. And the distance between the knife edge and the mass M, the knife edge and the new position of that mass M that make it to be balanced, you note it as your D2. And so you repeat the procedure for D1 equal to 7.5, 10.0, 12.5. That is what you have here. That means this your D1 will be constant. Then also repeat the entire experiment with the mass M completely immersed in water. When we are now immersing it in water, that is about this second diagram. That means we have to talk about density, upthrust, and all have you while discussing this part. And record the corresponding distance as D3. Okay. Now see what we do. From the principle of moment of forces, we noted that CG, that center of gravity, simply means the point at which the weight of that meter rule will act. The point at which the weight of the meter rule will act. Now, this meter rule that is 100 cm, mass of a meter rule, mass of 100 centimeter rule falls between 95 to what? 105 gram. Mass of 100 centimeter rule falls between 95 to 105 gram, depending on how light, how heavy, how stiff, how flexible that meter rule is. Are you getting it? Okay. Having noted this, if we are going by this now, from the rule of moment, we will say that the weight of this meter rule, we will take it in terms of mass. That means weight divided by G is mass, right? We'll call here to be, we are taking here to be 100 gram. 100 gram. If we are taking here to be 100 gram, that means it is accurate. Okay, because let's assume that it's not 100 gram. Let's take 98 gram. Let's say that the weight of this, the mass of this meter rule, that 100 meter rule is 98, because we say it's ranging between 95 to what? 105 gram. And so, if here is 98 gram, and the distance between here and here is 5. Now, this distance, we don't know it, but the mass we hang on it is 100 gram. Where is it? The mass of the steel here is 100 what gram. We call it mass of the steel, because the mass we use in the physics lab most time is in a steel form. In a steel form, something like this is in a steel form. Steel. Okay? And so we now say whatever is the position of this here, whether it is at the end or at the before the end, whatever is the position of this, the truth is that this mass cannot come to this side. This mass cannot come to this side to keep this body at equilibrium. That is just the truth. So whichever side it hang, we note it as our D2. And so that will take you to the formula that D2 is equals to what? D2 is equals to 98 times D1 all over the mass of the steel. Mass of the steel. So we have given several values for D1. All we need to do is that we put it here. 98 times what? 5. All over 100. We use it to get here. We also do it likewise. 98 times 7.5 all over 100. We do the one on 7.5. We'll do it again. 98 times what? 10 all over 100. We'll get this 10 ohm. We also say 98 times what? 12.5 all over 100. We get this 12.5 ohm. 98 times 15 all over 100. We'll get this 15 ohm. You get it? Then we'll press it in our calculator. 98 times 5 divided by 100. That is 4.9. This one will give us 4.9. We'll write 4.90. 98 times 7.5 divided by 100. 7.40 approximately. So we are approximating it to 1 decimal place, because the meter rule, the distance you are to get here can only be in 1 decimal place. It shouldn't be in 2 decimal place. Either it is as a whole number or it is in 1 decimal place, because the reading accuracy of a meter rule is 1 decimal place. That is 0.1 cm. Are you getting it? Okay. This one, 98 times 7.5. Okay, 98 times 10 divided by 100. 9.8. We have it as 9.8. Okay, and so we now say 98 times 12.5 divided by 100, 12.3. 98 times 15 divided by 100, 14.7. We have gotten our D2, the table for D2. Okay, using this. So this is about your D2, the first D2, the second D2, the third D2, the fourth D2, and the fifth D2. Now, how do we get our D3? How do we get our D3? The D3 make use of what? You immersing that mass in water. And there are a lot of things we need to consider here. One, relative density, upthrust, and all have you. And so first thing we will check is relative density. Relative density of the steel is equal to mass of steel in air all over mass of equal volume of water. Or all over mass of water displaced. First of all, get the mass of that steel. When you get the mass of that steel, there is what we call the Eureka can. The Eureka can. The sketch of it goes this way. So what you do with that Eureka can is you want to get the volume of water displaced. Let's say this to be the Eureka can. You fill it with water to this point. Then when you fill it with water to this point, you carry this steel, put it inside here. When you put it inside here, it will displace some water molecule. And when it displaces some water molecules, some of those water will come and what? Enter here. So you use this container to collect that water it displaced. Now this water it displaced, get the volume. Whatever is the volume of this water, assuming that the volume is 10 cm cube. Assuming that the volume of this water is 10 cm cube. Tell them that 10 cm cube is equivalent of 10 gram. Is equivalent to 10 gram. That is about 10 cm cube. The reason is because 1 cm cube is equal to 1 gram. That is what you now put as your denominator. So when you get the mass of steel in air using beam balance, chemical balance, you divide it with what? Mass of water displaced using Eureka can, for instance. And when you get the mass of water displaced, you now convert it to mass. When you get the volume of water displaced, you convert it to mass by saying that 1 cm cube is equal to 1 gram. You get it. So that means this is formula number 1 we need to make use of while sorting this. Then, after knowing about relative density, it is also important to note that upthrust you have been hearing about upthrust of substance in water. Upthrust of substance in water is equal to weight of water displaced. Weight of water displaced, and is also equal to mass of water displaced times G. Mass of what? Water displaced times acceleration due to gravity, because mass times G is weight. Okay? So we have to note that because we are going to formula derivation. Now, mass of, comparing this with what? This. We will now say that mass of water displaced is equal to upthrust of substance in water all over G. Remember here we said this times G, right? Times G. Let's write it well. So mass of water displaced times G is equal to upthrust of substance in water. And so mass of water displaced will now be upthrust of substance in water divided by G. We have to note that formula. Okay? Upthrust of substance in water times G. Now we want to note another formula, weight of substance in water. When you carry a substance and you put it inside water, let's say the water weighs 10 grams or 10 Newton in air. It weighs 10 Newton in air. When you put it inside water, will the weight be 10 Newton? If you check the weight using spring balance, will it still be 10 Newton? The answer is no, because of upthrust. You have to lose some weight to that fluid because it must displace some volume, some space. And so what we do here is we now record that weight of substance in water. Weight of substance in water so we now record that weight of substance in water, weight of substance in water is equals to weight of substance in air is equals to weight of the substance in air. Weight of the substance in air minus weight of water displaced. So weight of substance in water is equal to weight in air minus weight of water displaced. Okay? And so when you divide weight of substance in water by G, divide this one by G, divide this one by G, you'll be getting mass of substance in water equals to mass of substance in air minus mass of water displaced. Are you getting it? So everything will turn to mass. Okay? Everything will now turn to mass automatically. Yes. And when you get to this, there is something you need to do here. Recall that mass of water displaced is equal to upthrust of substance in water all over G. So this will now give you mass of substance in water equals to, what is the mass of substance in air? The mass is 100 gram. 100 gram minus upthrust of substance in water all over G. Okay, so mass of substance in water equal to 100 gram minus upthrust of substance in water all over G. Because mass of water displaced is equals to what? Upthrust of substance in water over G. Right? Now when you get to this point, you remember that density of a substance all over density in water is equals to weight of the substance in air, weight in air all over upthrust in water. Yes. How can we get our weight in air and how can we get our upthrust in water? Note that density of substance. What substance are we talking about? We call it a still. The substance, that still we use in performing experiment in the laboratory. It has a range of value. Each density has a range of value. Density of it is this range to what? 8050 in kilogram per meter what? Cube. Then in kilogram per centimeter, in gram per centimeter cube, you divide by 1000, 7.75 to what? 8.05 gram per centimeter cube. This is about the range of values of that word steel. Depending on how dense that steel is, that will determine whether it will have a higher value or a smaller value. And so let's pick this 8.05 as the density of the steel given to us. Now, taking that 8.05 as density of the steel, that means the substance we'll be talking about here is steel. That means the substance we'll be talking about is steel, density of steel. We will now remove substance and put steel. Density in water, because we are using gram per cm cube, we will be using all over 1 gram per centimeter cube, is constant. Then weight of steel in air. Weight of steel in air. Weight in air is equals to, weight of steel is in air equal to the mass, which is equals to 100 what? Gram times what? Times acceleration due to gravity, which is 980 centimeter per second square. So that will be giving you 98123 grams centimeter all over second squared. Okay, we now put it here. We now say that 8.05 all over 1 gram per cm cube. Density of water is 1 gram per cm cube. Is equals to weight in air 98123 all over upthrust in water. Therefore, upthrust in water is equals to what? In water equals to 1 times this 98123 all over 8.05. 8.05. And so when you compute this, you will be getting 12173 gram cm over second squared. That is the value of upthrust in water. But remember, mass of substance in water is what we have been working around to see if we can get it. Mass of substance in water, mass of substance in water equals to 100 grams, which is the mass of that substance in air given to us, minus the upthrust is 12173 all over 908, because the acceleration due to gravity is 980 in terms of centimeter per second square. And when you compute this, we have 100 minus bracket 12173 divided by 980. That will be giving you 87.6 gram. That will be giving you 87.6. That is mass of substance. That means when you immerse this substance in water, the mass you are to get will be what? 87.6 gram. And that will take us to how to get D3. We now say our D3 will now be equals to this mass of the meter rule, D1 times mass of the meter rule, which we take to be 98. We took mass of the meter rule to be 98 because we say it runs between 95 to 105. That is what we said. All over the density, all over the mass of substance in water, that is 87.6. So that is the formula we use. We'll put 5 there. When you say 5 times 98 divided by 87.5, that will be giving you, that means the first value is 5.6 cm. (5.60 cm). How did we get it? 5 times 98 all over 87.6. That means ordinary, as I want to run this video, I suppose to say mass of substance in water is equal to 87.6 grams. And some persons will say, how did you get it? That is why we are following the laws of what? Relative density, upthrust, density of a substance, to see how we can get it. Then this one, 7.5 times 98 all over 87.6. 7.5 times 98 divided by 87.6. That will be giving you 8.40. Right. You do the next one, 10 times 98 divided by 87.6. 10 times 98 divided by 87.6. 11.2. You also do 12.5 times 98 divided by what? Divided by 87.6. That will be giving you 14.00. And you finally do 15 times 98 divided by 87.6. That will be giving you 16.80. Okay, so we have seen how to get our table of values for this experiment. Now we want to go into graph plotting. Now these are the values we have gotten from this experiment. We want to see how to plot the graphs and answer these questions that follows. Okay, now how do we do it? First thing you do before you plot your graph is to write the date of your experiment. Write the date. Now after writing your date, write the title of the graph. A graph of, they say we are to plot D2 against D1 and also D3 against D1. A graph of D2 or D3 in cm against what? D1 in cm. So we are to plot D2 against D1, we are to plot D3 against D1, still on one graph. There are reasons why this graph plotting is asked to be plotted, and we'll see it. So we label the y-axis to be D2, D3, unit is in cm. Then we'll label the horizontal axis as our D1, unit is in cm. Then we have D2 values and D3 values. The highest is 16.8 and the highest is 14.7. So we need to make sure that while labeling here, it will cover 16.8. Are you getting it? Now, following all we have said about how to get best scale, appropriate scale, you just follow that pattern. But me, I will not be repeating it often time anymore. So what I will do is that if I say let here be 2, they didn't ask us to start from the origin or not, so I decide to start from origin because the least numbers are close to what? 0. Now watch. 2, 4, 6, 8, 10, 12. It cannot accommodate this, it cannot accommodate this. If I go by 3, 6, 9, 12, 15, 18, it can accommodate the 2. I can also go by 4, 8, 12, 16, 20, 24. So 3 and 4 can go for this vertical axis. I can write 3, 6, 9, 12, 15, and what? 18. Then for horizontal, the highest is 15. 2, 4, 6, 8, 10, 12, 14. 2, 4, 6, 8, 10, 12, 14. And the highest is 15. That means it cannot go by what? 2s. So what I will do, I can say let me go by 3. Okay, 2.5. 2.5. Then 5.0. 5.0, then 7.5, then 10.0, then 12.5, then 15.0. We use by 2.5. So it can go by 2.5 and this can go by 3. Now we locate our values. 5 against 4.9. 4.9 will be around here. If here is 6 and here is 3, in between there will be 4.5. So then 5 against, okay, 7.5 against 7.4. In between 9 and 6 will be 7.5. So then 10 against 9.8. In between 12 and 9, that would be 10.5. 10.5, and we are looking for 9.8, so before 10.5. Please, this is just a sketch of our graph. Just use this table and plot the graph accurately using your graph sheet. Okay? 12.5 against 12.3. 12.3. Then 15 against 14.7. 15 against 14.7. Okay? We have finished locating our words. Points. Then the next thing is for us to what? Take our words. Line of best fit. Now we have succeeded to plot the line of best fit. Are you getting it? You will notice that 2 points fall out on 2 sides. So we can manage it. We can manage it this way. We can manage it because at least they fall on opposite sides. This is your first line of best fit. First line of best fit. We also plot the graph of D3 against D1. D3 against D1. 5 against 5.6. 5 against 5.6. That should be somewhere here above this. Then 7.5 against 8.4. 8.4 above this. Then 10 against 11.2 above this. And 12.5 against 14 above this. Then 15 against 16.8. 16.8. Yeah, 15. So 16.8 should be here. Okay. And so we've succeeded to locate these points. So let's also get the line of best fit of it. Okay, we'll call this one L2, right? So in this, one fall this side, one fall this side, just close to the line. Whereas in this one, this fall here, and here fall here. Please be able to note. Let's circle this. This one is for the first one. This one for second one. Okay. All these first one, we are circling them so that we can easily differentiate it from the first one. This first one, we just circled and there are 5. But the second one, we did not what? Circle them. So this is what? So once you are done with this, ensure you indicate your scale. You can write your scale inside the graph, but let them be able to see it. On this vertical axis, we have that. On this axis, we have that 2 cm. 2 cm is that bigger boss. The bigger boss represents 3 centimeter. Then on D1 axis, we have that 2 cm represents 2.5 centimeter. So you also indicate your scale. Now, next is to get our what? Slope. Next is to get our slope. The first slope, we put our what? Straight line. We'll put our straight line. We'll say this is changing D2. Then this one, we'll also put for this. Change in D1. For change in D2, you say it is equals to, this is the highest, this is the highest is before 16.8. Look at this point is 16.8, but the highest is before 16.8. We can just take it 16.5, but when you do it, you get it accurate with your what? Graph sheet. Minus, you take this side is 5.0. For change in D1, it is what? 15.0 minus what? Here, this is 2.5. So we can take care to be about let's take it to be, let's say that this point 2.5, here is 5. Half of this is about 3.75, because this plus this is 7.5. So 3.75. Okay. So before the half, let's say here to be 3. So we now say this minus what? 3.0. But ordinarily, how to get the exact value you have here is that when this is your boss, and here is 2.5, and here is 5, it has what? 10 spaces. 10 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now what you do is 5 minus 2.5, you have it to be 2.5 all over the 10 spaces, 0.25. That means 2.5 plus 0.25, 2.75, the next line, then plus 0.75, 3.0, 3.25, 3.5, 3.75, 4.0, 4.25, 4.5, 4.75. So each of these balls is 0.25. So that is because this next one is 0.25. That is what we, okay, that means 0.25 plus this 2.75. Let's use 2.75. Okay, and so we'll have to compute our what? Slope. Okay, to compute our slope, we will tell them that slope, the first slope, is equal to 16.5 minus 5 all over the second slope, 15.0 minus 2.75. You press it in your calculator. 16.5 minus 5 divided by bracket 15 minus 2.75. You will be having 0.94. 0.94, no unit. No unit because here is centimeter and here is centimeter. They will cancel out. Okay? Then the next is you have gotten your slope. We now said they said we should multiply the S1 by the value of the mass. That is S1 times 100. We now said, well, for question II, S1 times 100 will be giving you 0.94 times what? 100 gram. And that will be giving you 94 gram. 94 gram. Remember, all we plotted here is just a sketch. Okay, just use your normal graph sheet and do the plotting so that you'll be able to what? Note this. And what do we call this? We will call this the mass of the meter rule. We will call this the mass of the what? Meter rule. We've been able to get the mass of the meter rule. We call this mass of meter rule. So please try to do this plotting well, deduce your values very well, get your slope very well, and be able to get your own slope so that we'll see what you get. Okay, this is just a sketch of it. Then we'll get the slope of the second one. To get the slope of the second one, we have to draw our line. We'll draw it. I just want to take it like this to avoid confusion. This one is change in D3. Why this is change in D1? For change in D3, we'll be having the highest is 14. 14 minus the lowest is 6. Then for D1, the highest is 12.5. We are taking this line minus where it meets here. Here is about 0.25, 5.5. Here should be about 5.5. 5.5. We say 5.5. We can take it as 5.5, but do the plotting so that you get the accurate answer. So we say slope of the third one, the slope is equal to 14 minus 6 all over 12.5 minus 5.5. What will it give us? We now say that it will give you 14 minus 6 divided by bracket 12.5 minus 5.5. That will be giving you 1.143, no unit, because this is centimeter and this is in centimeter. Now, after you have gotten your S2, just plot your graphs and be able to what, deduce this slope very well, accurately. We are just using a sketch. Now, they say calculate the volume. How do you get the volume? Volume, our length is length of the meter rule 100 times our L, our W is the width. The width of our meter rule is 2.5 times our thickness 0.5. You use your vernier caliper to measure from here to here and the thickness of the meter rule. So when you do this, you will be having 100 times 2.5 times 0.5, and that will be giving you 125 centimeter cube. So when you do that, you evaluate S2 times S, L times W times T. To evaluate it, I will say 1.143 times 125. What will it give me? It will give me the volume of that meter cube. We'll be having 1.143 times 125. That will be giving me 142.88 cm cube. So this is the volume of the meter cube, of the meter room. This is the volume of it, the volume of it. So how you do this is, when you are done with this graph plotting using your standard graph, this is just a sketch, but as you are looking at how everything is being done here, you can use it to work, plot your own graph and be able to get your slope as usual. Once you get your slope, say that your slope is this, multiply by 100 grams, which is the mass of the steel, to get the mass of the meter rule. That is one. Then get the slope of the second graph. Are you getting it? When you get it, then the volume is the total length of meter rule, which is 100 times the length of the breadth, distance of the breadth, which is 2.5, times the thickness using vernier caliper. We have it to be 0.5. Are you getting? Multiply them to get 125. Use 125 to multiply the slope you get for what? L2. And so if you are done with that, that means this is the volume of the meter rule. And when you now divide the mass of the meter rule by volume of the meter rule, you are getting the density of the meter rule, because the title of the graph says to determine the mass and density of the meter rule. So density of the meter rule is equals to mass you got, which you got by L1, slope of L1 times 100. Whatever you get here, you call it your mass, all over the volume. The volume is whatever you get in the slope 2, this L2 slope. Whatever you get there, you multiply it by what? Slope of, whatever you get from slope of L2, you multiply it to what? The volume of the meter rule, which is the length times the breadth times the thickness. So all over volume of the meter rule. And so when you compute it, you'll be able to get the density of the meter rule. So that is how to get this experiment done. What we did in the table of value is excellent, but for the graph plotting, because we did not use actual standard graph, we cannot say it is excellent. So use the actual graph and do the plotting. After plotting this, get your slope, multiply it by what? 100 gram to get your mass. Then get the slope of L2, multiply it by the volume, which is the total length times the thickness and times the breadth. Whatever you get, you call it your volume of the meter rule. Then whatever you get finally as your density, please use the comment box below and tell me what you get. Thank you once again for watching today's video. See you next time.